Okay, yes. Well, is a topic that at present is a hot topic in this domain. But before, I want to introduce just a small commercial. As I mentioned the RACAB. The RACAB is the Royal Academy of Science of Barcelona, where I'm a fellow at present. And it is in Barcelona at the Ramblas. This is the building, the central building. This is the Poliorama Theater that belongs to the Academy. And this is the Fabra Observatory that also belongs to the Academy. This Academy was founded in the 17th century in 1674, and the observatory was founded in 1904. So they have a long history, and it's just but it's not well known, and so I want to just to show that to you, and to start with my talk. Well, remember that the evolution of white dwarfs, we know, and this is presently clear, that for stars that have a mass that is smaller than 8 solar masses, they end their life as a white dwarf, a carbon-oxygen white dwarf. Concerning the star with a mass in the range of 8 to 12, they have two options, and one is to end as a white dwarf, and in this case is an oxygen neon white dwarf, the chemical composition of the interior, or they can collapse via electron captures and to give a supernova. And for instance, it is suspected that perhaps the Crab Nebula or the supernova associated to the Crab Nebula, the mechanism was this one. The evolution of these stars, of white dwarfs, is just a cooling process that with some problems. Here we see the evolution of 0.6 solar masses white dwarf, in which we see that at the beginning, when the white dwarf is born, the main source of energy is hydrogen burning in the outer layers. This is around the planetary phase. Then rapidly, this burning is quenched, and then we have a strong emission of neutrinos. And then finally, when the temperature is low enough, neutrinos stop being efficient, and then the white dwarf cools just by the emission of the latent heat at the interior. So the situation we have is a core that acts as a reservoir of energy surrounded by two layers, or an envelope, if you prefer, that is partially degenerate and controls the flux of energy outside. This is the main idea. The origin, the initial conditions of white dwarfs are not well known. We are not able to model the AGB phase correctly for the moment. So we have a broad range of initial conditions. Fortunately, as soon as neutrinos control the evolution, all the thermal structures converge to unique one. This unique one can be approached by an isothermal core, and this envelope that is it's not easy to model, but it's comfortable to approach with several analytical approximations. So during this process, we have these phases. One is the neutrino cooling that stops around a luminosity of log minus 1.5. Then we have a fluid cooling in which the interior is a Coulomb plasma that behaves like a liquid, and this lasts from minus 1.5 to minus 3. And then when we arrive to such luminosity, the plasma starts to crystallize. During the process of crystallization, we have two additional sources of energy. One is the latent heat, that is relatively small, is of the order of the temperature in units of energy of solidification. And another one that is more subtle, in which when we go from the liquid to the solid, the solubility of the components changes. So we form a solid that is enriched in general, we will see that, for instance, the heavy elements, and this sinks, and this releases important amounts of energy. On the other hand, from the aspect of the white dwarfs, is quite complicated. And here is the classification of white dwarfs very quickly. In general, we have those that are called DA, D from degenerate, and A because we can detect in the photosphere the hydrogen lines that go from a temperature of the order of 90,000 degrees to 6,000 degrees, and below such a temperature, the spectrum is almost flat. We can distinguish almost nothing. In fact, in the stars, they are used sometimes to calibrate the black body. The DOs, they have a spectrum that is dominated by helium. The temperature, it can be very, very high, 100,000 degrees. It goes to 40,000 degrees. And we can see some traces of carbon, nitrogen, and some metals. And some of them, of the coolest, they are hydrogen poor. Then we find the DB, they go from 30,000 to 12,000 degrees. Notice that there is a hole between 40,000 and 30,000 degrees that is called the DB gap. Then we go to the DQ that are dominated by helium. The temperature will go from 12,000 to 6,000. And then we have the DZ, where this one only show metallic features like that and nothing else. And then we have the DC that they are so cool that the only thing we see is a black body. There are no features here. And then, of course, there are the subtypes in which we see that some of them, they have metals. They are DA with metals, DBZ with metals, with pollution, and something like that. So from the phenomenological point of view is quite complicated. And the reason is the following one. The gravity is very strong. It's of the order of 10 to the 9 in CGS units. Then this means that the heavy elements tend to sink and the light elements have to float. So after a very short time, we form a stratified structure with helium here, hydrogen here, and here the core made by carbon oxygen in general. And along the evolution, there are several phenomena that tends to restore the homogeneity. One is radiative levitation. When the star is very hot, the radiation is enough to push the heavy elements towards the surface. And then when the radiation goes down, then they settle once more. In the interface between the two layers, we have always atomic diffusion. And then we have also when the star is cooling off, when the elements start to recombine, then we have convection in which these layers tend to mix. To that, we have to add that when it's very hot, we have some wind that especially affects the heavy elements, and we have accretion from the interstellar medium, but especially from the remaining of the planets that survive to the AGB phase. So by analyzing these elements now, we can infer which was the chemical composition of the planets that were orbiting the star. This is one of the points of interest. The evolution, very quickly, is the following one. In principle, we have two families, the DAs, which show hydrogen at the surface, and the non-DAs that where hydrogen is absent. And they proceed from two families of stars, from two initial conditions. One in which we have like that, it goes, the hydrogen floats to the surface. We see only hydrogen, the star cools down, and there is a moment where we have convection, and then this hydrogen mixes with the helium layer, and then it disappears. And so the star migrates to the non-DA family. And that depends on the total amount of mass in the hydrogen layer. The non-DAs is much more complicated. In this case, we start with is dominated by helium, but there is some hydrogen in the interior. Hydrogen floats and forms a very thin layer around the star. And so the star moves from the non-DA to the DA family. As the star cools down, we have convection one more. This thin hydrogen layer mixes with helium, and then we see a DBS star. And then as the cool down, we are finding all the other families that we have seen. And then polluted and all these things. And so here we have a contribution from the non-DAs, the original non-DAs, and here we have a family that is the original DAs, but they are migrating. There are other things that can introduce changes, but I'm not going to enter here. So for the moment, we understand, grosso modo, which is the evolution of these stars, but there are several shadows. The two main problems that is common, I think, to all the stellar evolution are the origin and evolution of the magnetic field and the origin and the evolution of the angular momentum that for the moment is not understood. We know, I'm going to talk about the magnetic field, and we know that these white dwarfs, they have larger scale structure, and very often they are dipole-like. Apparently, they do not evolve during the cooling process. I mean by that if we have a star, the magnetic field remains almost constant during the evolution, not the number of white dwarfs, but the intensity is in the range of the kilo-Gauss to the giga-Gauss, so it's quite large. And there are differences between the properties in single and binary white dwarf. So the questions that we have is, which is the origin of the magnetic field? Why the magnetic field only exists in a fraction of the individual white dwarfs? Which is the difference among the different magnetic waves, the difference in single and binary systems? These are the three questions, the three central questions that we have. The observational status has changed abruptly during the last 2 years. Until the 1920, more or less, I see, what we know is that, or the general ideas were the magnetic white dwarfs, they are more massive than non-magnetic white dwarfs. This, I advance that this is not completely true, or it has to be specified. Second, cool white dwarfs are more often magnetic than hot white dwarfs. The magnetic white dwarfs are not found in closed binary systems in which the companion is main sequence stars. I mean that you have a binary system, you have two stars, one is a main sequence, the one evolves to white dwarf, and then if this white dwarf is young, we don't see a magnetic field, or rarely we see magnetic fields. When we enter into the cataclysmic variable, then we start to see magnetic fields. And the other thing is that DQs, if DQs are very cool and they show the presence of carbon at the surface that probably has been dredged up from the core, look as in them the magnetism is more frequent than in the other stars. And the big question is, are these trends representative or are just a consequence of observational bias? Well, before entering in details, I'm going to present which are the theories trying to explain the origin of the magnetic field. This essentially, a magnetic field can be obtained in a star, may have two origins. One is just inherited. There was the parent of these stars were magnetized, and we have a conservation of the flux, and then we have this flux. Or we have, in the long evolution, we have a dynamo that is working. So one is the fossil hypothesis, and this one, it was assumed that they were the descendants of the A and B magnetic stars in the main sequence. The other is this magnetic field has a binary origin. And the moment of forming the star, they interact, they have a common envelope, and in this common envelope, the other possibility is that we have two white dwarfs. They approach by the emission of gravitational waves, and they merge. During this merging, what happens is that you are not losing mass, and in this case, the system is gaining, or the star, the merged star is gaining all the angular momentum, so we have also another dynamo. Another possibility is in autochthonous origin. Once the white dwarf is formed, some convective regions appear, and then we have also a dynamo, see if the star is rotating. We have two possibilities. One is a dynamo at the surface, when these helium and hydrogen layers, they ionize and they become convectives. And on the other one is when you have the crystallization, where there is a change of solubility, and then this difference of solubility produces a compositional driven convection. So these are the mechanisms that have been proposed up to now. Concerning the origin of the magnetic field, the fossil hypothesis, initially from the first moment, it was, remember that the magnetic fields were discovered simultaneously in white dwarfs as pulsars. So the attractive of the pulsar, the image of the pulsar, it was very strong. So it was accepted, or was proposed, that these magnetic white dwarfs, they were the descendants of the APVP stars. And in fact, if you apply the conservation of the flux, and you take the flux of these stars, you see that effectively you can reproduce what is observed, more or less. The second question is that these stars, these APVP stars, when they form a white dwarf, the mass of the white dwarf is of the order of 0.8 solar masses, that is of the order of the excess that we see for the magnetic white dwarfs. But there are several questions. The first one is, are there enough AP magnetic main sequence stars to account for the observed abundance of the observed fraction of magnetic white dwarfs? This question, just up to now, it was clear that no, because the incidence, as we will see, the incidence of magnetic white dwarfs is of the order of 25%. 22 plus minus 2%. And these stars, APVP, can only account for something of the order of between 5–10% at maximum. The question is that recently it has been discovered that the main sequence stars, they are magnetic too, and magnetic fields. For instance, it was a surprise for me, from the asteroseismology, in the interior of the sun, we have a magnetic field of the order of as large as 10 to the 7 Gauss. We have the tachocline, and we have the convective layers. So the question is, the sun is going to provide a magnetic white dwarf at the end or not? The other thing that is also interesting is that when we have a red giant, this is the helium core. Here we have the burning. Here we have pressure waves. Here we have gravity waves. And from the interaction of both, we can understand the behavior of these red giants. And this was a surprise because it was not expected at all. So we have plenty of stars that at the end they can produce magnetic white dwarf. And now the problem is, I think, is a really intriguing problem, is what happens with these magnetic fields along the evolution of the star. Can they survive the process of formation of the white dwarf? And if they survive, are they confined to the interior, and how the magnetic field migrates towards the surface? This is the big problem for people working in stellar evolution. The other possibility that I mentioned is the evolution of a binary star. We have a binary system, we form a common envelope, then we start to transfer angular momentum to this common envelope, so we form convective regions, and then we can produce a magnetic field. And then here we may have two solutions. Both the stars, they merge to form a unique one, then it follows the evolution, the normal, more or less normal evolution, and expels the outer layers, and we have an individual star with a magnetic field. This is one of the possibilities. The other possibilities is that during this process, the evolution is lost, we form a binary, and finally, this binary is a magnetic binary that evolves to the formation of a cataclysmic variable, and then we see a magnetic field produced during this process. Which is the problem? That magnetic fields in this region are not seen. Only here. So this is the reason why this model is not very popular, for me at least. The other model, that is the one that we computed with error, is the merging of two white dwarfs. In this case, what we have is we have a binary, then the primary evolves to a red giant. We form, as before, we form a common envelope. This common envelope expels the outer layers, and we form a white dwarf plus a normal star. And then we have a plethora of situations. We can form, depending on the parameters of the system, we can form cataclysmic variables, supersonic ray sources. This can finish as a type 1 supernova, and so on. But one of the possibilities is to arrive to the formation of a double degenerate, that they are close enough to merge by the emission of gravitational waves. If they do that, what we form is such a structure. We have the primary with a temperature that is rather high, 10 to the 8, surrounded by a disk. The total amount of mass that is lost is very, very small. This was the thesis of Josep Guerrero. And then we have here very strong gradients of temperature that produce convection. And all these things is spinning very quickly. So we can form here, we can prove or can show that this magnetic field cannot migrate towards the interior. It doesn't migrate towards the exterior very quickly, at least, and then we can remove angular momentum with the winds, magnetic fields, and so on, and reduce the velocity to very efficiently the velocity of the system. So the prediction is not necessarily a very rapidly rotating system. Well, one thing, all these theories, in principle, they are pros and cons, and they are appearing and disappearing periodically. The third situation is in which the star is cool enough, then hydrogen start to ionize, helium start to ionize. We have convection in the outer layers, so with rotation, we have a dynamo. The problem in this situation is that the field that we can produce, because there is not enough energy, is only of the order of 10 kilogauss or smaller. So certainly it cannot account for all the systems. The other mechanism is the one that I have been working during the last years, is the one related to crystallization. In this case, just remember one thing. This is the phase diagram, and here we have the chemical composition. We have is oxygen. Here I represent the abundance of the heavy element, hydrogen. This is a diagram that is called of the spindle form, and you have a liquid that goes down like that. It arrives to what is called the liquidus, where the start to solidify, and the solid is that is in equilibrium with this liquid has this composition and this temperature. So it's enriched in this case in this element. And since it's enriched in the heavy element, it sinks. And a liquid that is poor and lighter is left. So the result is that we have potentially unstable radiolateral instability. Another possibility is depending on exactly the components. And in fact, this is the case. We may have an azeotrope. This is what happens with alcohol and water in the liquid case. When you arrive to the 97 degrees, you cannot separate both. That the azeotrope is here. The two components are completely miscible. Then if the abundance of the heavy element is in the right, we have the same behavior like here. We form a solid that goes down. But if you are here, we have a very interesting situation in which the solid that we form is lighter. So we have snow that goes up. And at the end, it mixes somewhere. And if it is lighter than the environment, it mixes by a radiolateral instability. So we have some kind of depuration system in which we are distillating the matter, and what we obtain in the center is this chemical composition, the azeotrope, because we cannot separate them. Well, this is a variant, and I'm not going to enter into that. So take now carbon and oxygen. We are going to form a solid. We are going to form a convective zone driven by the chemical composition. We are going to have a conductive mantle, and then we are going to have the helium envelope and the hydrogen envelope. So the situation is entirely similar to the Earth, where we have a solid nucleus, we have surrounded by the liquid nucleus, and then the solid mantle, the rocky mantle. The evolution is the following one. For instance, this is for one solar mass. We have the evolution of the solid core that it grows. And we have here the position of the outer envelope. And we see that this depends on the detailed chemical composition of a star. We see that we have this behavior, and this envelope, in the case of the 0.6 solar masses, what we see is that the outer layer stops at 0.9 the surface. So the magnetic field has to overcome this difference to emerge. Solidification also depends. In the case of one solar mass, it starts at minus 2.5 because the density is larger in the center. In the case of 0.6, it starts at minus 3.6. And the energy that you can release, depends on the gravity field, is between 10 to 12 to 10 to 9 x per second. The second step that we did was the following one. In 2010, Christensen provided what is called a dynamo scale theory, in which what is trying is to relate the properties of the dynamo with the physical properties of the environment. And for instance, the energy, the magnetic energy, is proportional, it has shown that is proportional to the fraction of dissipation, ohmic dissipation, times the time scale of the system. This is L is the size of the dynamo region, and eta is the magnetic diffusivity. Q is the flux of heat transferred by the convection, and HT is a typical thermal scale of the star. Well, after operating, you can integrate over all the star and to obtain the total energy that you can have per unit time. And what is important is that what they found, or he found, is that if you plot this energy per unit volume with the intensity of the magnetic field, here we have the Earth, here we have Jupiter that has a similar structure or similar origin of the energy. here we have the Tauri stars, and here we have the M dwarfs. So the question was, can these scattering laws be applied to white dwarfs? Well, certainly not, but you have to try to see what happens. Well, certainly with some conditions. This is what we compute. This is the release, the evolution of the energy per unit volume as a function of the luminosity for different solar masses and different chemical composition of the outer layers. And then when you do that, you see that white dwarfs, they are placed in three regions. Here, the open circles are the more massive. The red ones, the are those with a helium layer. And then what you see is that the DAs follow the Earth Tauri line, but they can only produce magnetic fields that are of the order of 1 megagauss or a bit less. But we have a family there which may have different values. The way I obtain that is just integrating these equations of structure with the models. So the models could be not correct. The second question that you can pose is the following one. The diffusion time of the magnetic field under such conditions is extremely long, is larger than the universe, the age of the universe. So the question is, notice that the total amount of energy that I can release in this system changes a lot with the luminosity. So if the field that I can create at the beginning remains, or perhaps what is representative of the magnetic field, or the final magnetic field, is the initial field that you obtained. When you put that here, the situation improves a little bit, and we see that we have these stars within this one, and a new one here with a new different constant, but similar profile. And well, this is the status of that. We launched these ideas in 1917. There was a colloquium in Los Alamos about this physics. Unfortunately, I have not been able to go there, but as you can see, the criticism was quite strong. This was Andreas Reiseneder from Chile, and he claimed that, well, this is extremely good for me, at least. Our model can be falsified. So this is something that cannot be said on all the astrophysical theories, but there are several arguments in con. The first one is that our mechanism predicts the formation of the magnetic field quite late, when the star is cold. We cannot reach, as we have seen, the strongest field, the strongest fields. But we have two families. The blue dots had a very, very strong field of the order of 200 megagauss at least. It's difficult to get B to the surface, but as we have seen, it depends essentially on the mass of the star. The different incidence of B in single stars and binaries. But this is another question that we can talk another moment because I have no time. And this one, I don't agree at all. That is, requires different mechanisms for other star types. Of course, in science, it's always good, especially in astrophysics, to have a unique mechanism to explain different objects. But this is not a necessary condition. It's the physics that unifies things. And we know that for a magnetic field, the two rules are conservation of the flux and dynamics. And so what we have to see is what happened with these two properties of the magnetic fields, not to put the condition that the conservation of the flux is the only mechanism to produce a magnetic field. So the question is that we have to compare theory with observations. And here is where the problem starts. is quite difficult to detect magnetic fields. First, we do that by Zeeman effect. So if the magnetic field is moderate of the order of between 3 or 5 to 100 Gauss, then we split the lines and they are quite clean. But as the magnetic field becomes larger, the energy of the magnetic field starts to change all the orbitals of the atoms, or of the ions, if you prefer. And so we have here something that is almost impossible to disentangle. This is in the case of the very strong magnetic fields. If they are weak, then the problem that we have is another one. If they are weak, we have stars, white dwarfs, with a large gravity, large pressure. So this means that the lines, they are very broad by the Stark effect. If you have here in these broad lines, you introduce the Zeeman effect, then you have something that is impossible to disentangle. And this is the case. So it's very hard to detect weak fields. And the other possibility is just for the polarization. But this demands is not easy, and it demands a strong dedication in time and work. The problem then is that the majority of the magnetic white dwarfs, now the population is of the order of 800 magnetic white dwarfs, is that they've been detected in surveys that they are not devoted to white dwarfs, the SDSS and something like that. They have a very small signal to noise, and they are especially sensitive to the Gauss. So there is a strong bias. As a consequence of such a strong bias, the common ideas were we have the majority of stars, magnetic white dwarfs, in this range. Then we have a small population here that it was believed, and there was a bimodal distribution. Here there was a gap, and here there was some population. There was almost a rather agreement that there is a limit here. This is residual. Then, thanks to Gaia, it has been possible to build the population of a complete population within the 20% around the sun. When you make that and you make a detailed analysis of the magnetic field, the situation moves from that to a flat distribution. And there is a very recent, this year, a very recent reanalysis of the SDSS sample. It is very well done. And then what they have found is that effectively this number increases very high. So if this increases and it is flat, perhaps the population is quite large. The second question that was discussed was the incidence according to the different spectral type. We have seen the A, the Z, and so on. Here is the distribution, the probability distribution, and if most rapidly, if you go to the average distribution, you see that we have the DAs, that they are dominant because they are the more abundant and they are easy to analyze. We see that DAZ, they are slightly underabundant but compatible with the DAs. DA plus DZ is perfectly compatible because these are DAs contaminated. The disease, there is a deficit, but remember that the disease, they have a continuous spectrum and it's very hard to observe. So probably it is a observational deficit. We have the disease, this is an excess, but also in this case, it's very easy to detect the magnetic field with metallic lines. So this is favored. The DQs happens the same because the presence of carbon, then it's easy to detect the molecule of carbon. And finally, we have the average like that, and is of the order of 22%. We think a sample that is complete. Also, when we look for, well, this is a distribution with the temperature and with the mass, and when we see that with the mass, what we see is that you have two peaks, one at 0.8 and the other at 0.6. There is the number of white dwarfs here in the cool ones effectively is a bit larger. Here, if we have the mass and the intensity of the magnetic field, we see also that there is not a preference, but the more massive white dwarfs, they may have large fields. And from here, you can see that the average mass of the magnetic ones is larger than the average mass of the non-magnetic ones. That is, I would say, but this is changing. Well, you have here the same with the age, and if you are done losing mass during the age, this we see that this is almost constant. That was star. This is not the number of white dwarfs with the age, but is the evolution of the intensity of the field with the age, and you see that it remains almost constant. And this is due just to the fact that the diffusivity of these magnetic fields in the star is very small. With rotation, in the case of rotation, well, it's very difficult to obtain the rotation velocity. It can be done photometrically or spectrophotometrically. But what is interesting to see is two things. First, magnetic white dwarfs, they are relatively rapid rotators. The period of rotation is much smaller than that of non-magnetic white dwarfs. The second is that we have here a cluster of very slow rotators with a very high magnetic field. And one of the possibilities is that they are the product of the merging of two white dwarfs that create a very strong magnetic field that slows down the rotation of the system. But notice that this is of the order of 10 to the 6 seconds is a non-rotating object. And probably what is more important is that the age. Well, one of the problems that has to be overcome is that usually we started with magnetic limited samples. So we observe stars with a given magnitude. So you can reach, depending on the magnitude, you can reach different volumes. And when you see that the young objects are brighter, they are favored by magnitude limited samples. Why you use a volume limited, then the situation is more stable. Then in this case, what you see is that this is the number of magnetic white dwarfs versus the number of white dwarfs in the bin. So you can see here that there is a drop in the abundance, and that is increases. So there is a deficit, a real deficit of young magnetic white dwarfs. And just to finish, the last situation is this one that is a bit complicated. Well, here in this part, here is all the stars that they are obtaining within from the sample obtained from a volume of 20% of radius. And here, there in this the left, in the upper layer, is the number of stars that have been obtained with the sample of 40%. But they are very bright and young. And the nomenclature, I don't know if you can see very well, but you see that the circles, they are non-magnetic stars, and you see that it's strongly populated. Dots, single dots, they are stars with a magnetic field smaller than 1 megagauss. And you can see that they are few ones. Then dots without circle is from 1 to 10 megagauss. With two circles is 10 to 100 megagauss, and with three circles more than 1000 megagauss. And what you see is that here in the region, is populated by young white dwarfs. Here, by young white dwarfs with an age that is smaller than 0.5 gigayears. So they have been formed very recently with a very high magnetic field. They are very hot. And here, what you see is that we have a few magnetic white dwarfs, and the strong white dwarfs appear at the right of these two lines. And these two lines represent the crystallization frontier. So here they are crystallized, here they are not crystallized. So we have two populations. Low mass white dwarfs, that they are cool, and they have crystallized with can be very strong. And there we have very young white dwarfs, massive, with a strong magnetic field. So, which is the situation? Young white dwarfs, we see those which have a mass that is 1.1 solar masses, the 85%, they are magnetic and have a field that is very strong, between 3 to 300 megagauss. And on the contrary, if you consider the stars with a mass that is smaller than 0.75, only the 2.5%, they have a magnetic field. It is clear, therefore, that the crystallization plays a game here. In this graph, you see here it is the cooling time for the white dwarfs, and you see that the number of white dwarfs increases as the total number as the cooling time grows. Here is the same, but instead of the cooling time, we have the cooling time versus the moment of crystallization, because the crystallization can occur at different times. And then you can see that there is a slow growth, then a sudden increase. And this decrease is just due to the selection effects, because it's very hard to detect these cold magnetic fields. So I insist crystallization plays a game here. Very recently, now in January, it has been analyzed all the non-white dwarfs at 100% of distance. Is not necessarily complete, but you can see here the red dots are the magnetic ones. You have here the mass, and here is the band of crystallization. One is when crystallization starts, the other is when crystallization is almost finished. And you can see that almost all these magnetic white dwarfs, they are in this region. So crystallization, I insist, plays a game here. And the game is which one? In our initial paper, we assume, and I'm going to finish with that, we assume that when we crystallize, we instantaneously form a solid plus a carbon liquid. So this means that the contrast in density is when the gravity is very, very strong. We have a very violent turbulent flows, velocities of between 30 100 kilometers per second for the Dwarfs. This means that if we have a strong buoyancy and we have a slow rotation, the dynamo is not efficient, and so we can only produce a strong fields when saturated in the case of very rapid rotators. This has been reanalyzed by Ginsburg last year, and then what he did is to remove this weak hypothesis, because when we start to form the solid, we are releasing the light element, but this is not instantaneous. So the solid is surrounded by a liquid that is progressively lighter and lighter. So there is a moment at which this starts to become really stable. So you have to wait a characteristic time that depends on the size of the crystallizing region and the conductivity. When you introduce such effect, the process is slower because the contrast intensity is smaller, and then we have a very efficient dynamo. The third analysis is Fuentes in January, then Fuentes et al., which have modeled this behavior, not only for the center of white dwarfs, but also for the crust of the neutron stars, because the phenomenon is the same. And what we have found is that there is not enough, in the process, there is not enough contrast, there is not enough energy in the form of kinetic energy to fit the dynamo. So if they are right, they kill the dynamo, they kill the crystallization as a dynamo. And then this is the problem. Now it becomes the problem, it becomes even more interesting. Crystallization plays a role. Which role? If carbon-oxygen mixture, and here there is an if concerning that. If carbon-oxygen mixtures cannot activate the dynamo, which is the responsible of the dynamo? One possibility is neon 22. Neon 22 is produced by the alpha burning of carbon, oxygen, and nitrogen, the initial content. And then since it has an excess of neutrons, they have the tendency to go down. But at the same time, there is an aziel drop. And so in the case of neon 22, we have bullets of carbon oxygen rich that are lighter and they go up. And so this analysis will not apply. And the total amount of energy that you can release like that is enormous. And this has to be analyzed, what happens. What is also interesting is that in this case is metallicity dependent. And so this has some implication in the evolution of the galaxy. The other possibility is that if we have convection anyway, then this can modify the migration of the magnetic field and help the migration, the magnetic field from the inner region to the outer regions. And here there is also a problem for the people working in type 1 supernova. If we have a very strong field in the interior, the burning regime in the interior is completely modified by the magnetic field. And so if this is the case, we may have interesting consequences of that. Well, I stop here. I think it's perhaps too long. But these are the conclusions. The conclusions.
Okay, thank you, Jordi. Now we are almost running out of time, so probably we have 2 or 3 questions from the audience. And then
Thanks a lot, very interesting. I have a question about also in comparison with the plot of the sun that you showed in the strong sort of internal field and the lower outside. In comparison with white dwarf, how well do we know or can model or can detect, I don't think detect, let's say, the geometry of this? So when you speak about white dwarf fields, I guess you're speaking about a dipolar geometry, right? Or not? Or do we know something else?
Well, I am not following in detail that. There are work by no, Spitzer, but no, I will tell you. In principle, there are indications that the magnetic field is effectively dipolar, and then tends to evolve to a dipolar field with some substructures. But I can say nothing. I'm not competent on that. I can look for some literature because but the tendency is to migrate to a dipolar structure. from what I have read.
Very nice, Jordi. Really interesting. I have many questions, but I will just make one. Can you go to the plot of distances, the scaling laws for dynamo? So if I understand correctly, you try to place there the white dwarfs from the models, right?
Mhm.
You cannot in any way like place the observed ones in that plot.
No, sorry, no. They are the observed
Yeah,
ones. But the observed ones, what I have is the temperature, the mass, the physical properties they will obtain from the Gian-Michele catalog. And then I fit the observations with the model. And then I apply the Christensen.
Okay, to obtain the flux.
Exactly.
Okay. Yeah, because this is just a comment that about that scaling law that is very famous. Very recently, there's some observation of ground dwarfs, so in the left side of the data, that are outside this law. So they have fields that are similar to M dwarfs. Why they should be one order of magnitude lower. So this scaling law is very good, but there are some objects that don't respond to that. So it's normal to have some deviation.
Well, in fact, the Christensen scale, it cannot apply to everywhere in any way. That is partially what I did. But because, we did that when we started. And in this case, the question was the reverse. Can we apply the Christensen laws to a situation that is quite similar? In fact, the characteristics, the prime number, the magnetic Raynaud numbers, they are very different from those of the Earth. But it's not an easy. Well, the region in order to model that is in the worst part of the dynamo systems. But the advantage is that we can compare our models with observations and constrain the numerical models.
I don't know if there are any questions from the participants through the Zoom. Hello?
May I ask a quick question? Thank you for the nice talk.
Yeah, please.
Yeah, I just want to, I didn't really get what is the problem with these models of the stability of the field, because the field, are you saying that they have not enough time to reach the surface once they go unstable?
Yes, in fact, we don't know how the initial fields evolve first. Do they survive the Reggian phase or the AGB phase? And then if they are internal, which is how they emerge, because when you look to the characteristic diffusion time is extremely slow. So they are confined.
Well, unless they get some MHD instability.
They get some?
At least they get some instability, because these stars are, these objects are fast rotating. So some instability must be stabilized, must be suppressed, but other secondary instabilities may kick in. Am I correct?
I miss.
Yes, we miss you.
No, that when these objects are really fast rotating, so the instability of toroidal field is suppressed, must be suppressed for fast rotation, but some other kind of instability like MRI, for instance, may show up. So we don't really know what happens there. And this may allow to reach the surface.
Yeah, sure. But this is something that has to be modeled, that to my knowledge, it is not satisfactorily modeled for the moment.
Yeah, absolutely. I totally agree.
Okay.
Thank you.
Thank you. Okay, then thanks again, Jordi, for your talk, and thank you all for your attention. So probably we move to the panel for the pizza, no?
Yes.